Hello and welcome to my course in Transformation, Semigroups and Application. I'm Dr. Imam, a lecturer in the Department of Mathematics, Ahmadu Bello University, Zaria. This is the third lecture of the course, and in this lecture we are going to talk about finite full transformations. In the last lecture we introduced the concept of partial transformation of a set. We also define the full transformation of a set that is not necessarily finite. Here we are going to concentrate on the structure of finite full transformations. So if we consider a set Xn to be a finite set of n element consisting of element 1, 2, 3 up to n, and write Tn for the full transformation semigroup. In the last lecture, we say the set of all full transformation on a set X is denoted by Tx. Here we should write Tn for the semigroup Txn. Instead of writing Txn, we will be writing Tn. Then for each alpha with R element in the image set, every such alpha is written in the array form as alpha equal to A1 mapped to A2, A1 mapped to B1, A2 mapped to B2, up to AR mapping to BR. This is the array notation we introduced in the last lecture. The only difference here is the fact that we are dealing with a finite set. And when you are dealing with a finite set, that means the number of blocks must be finite, and this block is forming a partition of the set Xn. So if we take the union of A1, A2 up to AR, then we have the entire set Xn. This is actually what it means to be a full transformation, because for a full transformation, the domain of the mapping should be the entire set, as we have it here. Now, we can count how many elements are in Tn, because we are in a finite situation. Then we expect the number of elements in Tn to be finite, namely the order of the semigroup. So the order of Tn is n to power n. And to see that this is actually the total number of full transformation from the set Xn to itself, one can visualize a partial transformation as a mapping sending element of the domain to element in the codomain. But since we are dealing with full transformation, the domain is a set 1, 2, 3 up to n, because that is our underlying set. And the codomain will consist of the images. In the last lecture, we introduced the notation, and we said we don't write elements that do not appear in the image. So we only concentrate on elements that are images. So you think of a full transformation as a mapping sending a point of Xn to an image. And so therefore 1 will map to its image, which we denote by 1 alpha, and 2 will also map to 2 alpha, 3 will map to 3 alpha, and n will map to n alpha. But this 1 alpha, 2 alpha, 3 alpha, and n alpha, there can be any point of the set Xn. There may be repetition here because 1 and 2 can map to the same point in the set Xn. So what we are depicting here is not exactly the image set, but repetitions may occur. So we are seeing the images of the point in the domain. And so this is a way to visualize a typical full transformation in Tn. But since we are interested in knowing how many elements are in the full transformation, then we can count the possibilities of choosing an image for 1 alpha here. Because you have n element in the set Xn, then you can take any of the n element and insert here to serve as the image of 1. So you have n possibilities for choosing the image of 1. Likewise, there are n possibilities for taking the image of 2 and n possibilities for taking the image of 3, and also n possibilities for taking the image of n. That means we are counting the number of possibilities, in other words, degrees of freedom here. And so since every choice of an image can go with the remaining other choices of the image, we see that the total number of mappings in the semigroup Tn would be to multiply these numbers out. So you multiply the possible choices for the image of 1 with the number of possible choices for the image of 2, and times the number of possible choices of the image for the image of 3. And then once you multiply all these numbers out, you get the total number of maps in Tn, which is now n times n times n, n times, and that gives n to power n. So this is how one will now see why the total number of the full transformation in the semigroup Tn, that is full transformation on the set of n element, is equal to n to power n. So now we want to study the structure of the individual element in Tn. That is, we want to concentrate on a particular element in Tn. Now looking at an alpha in Tn, we can associate with each such alpha in Tn a directed graph, gamma alpha. And this directed graph has as vertex set the set xn, and in the graph there will be an edge from a point I to j if and only if j is the image of I under alpha. So this is how you define the graph. The vertices of the graphs will be the point 1, 2, 3 up to n, and there will be an edge from I to j if j is the image of I under the mapping alpha. So every map induces this type of graph. And so looking at example, if we pick this alpha from T8, then the digraph associated with alpha is as follows. So first of all, you have the vertices 1, 2, 3, 4, 5, 6, 7, 8. These are the vertices of the graph, element of xn. And once you have the vertices of the graph, then you can start assigning edges, directed edges. Because 1 is mapped to 1, there will be an edge from 1 to 1, namely a loop. And then because 3 is mapped to 1, we have an edge from 3 to 1. Likewise, there is also an edge from 2 to 3 because there 2 is mapped to 3 under the mapping alpha. And then we have edge from 5 to 3 also. And we can see here 4 is mapped to 4, so there will be a loop at 4. And 6 is mapped to 4, so we have an edge from 6 to 4. And then 7 is mapped to 6, so there is an edge over there. And likewise, there is an edge from 8 to 6. So this is the associated graph with this particular alpha. So in a similar way, whenever you take a mapping alpha, you can always develop a directed graph whose vertices are the point in the underlying set xn, and there will be an edge from a particular point to another if that point is mapped to the other point. So this is how we define, we associate a directed graph corresponding to every alpha. So with this concept, we can define an equivalence relation corresponding to, again, with every alpha in Tn, such that the relation tilde alpha on xn defined in the following way. So x, 2 points from xn will be related. X is related to y if and only if there exists s, t, non-negative integers, so that x alpha s is equal to y alpha t. Meaning you can apply alpha on x a certain number of time and arrive at the same point on application of alpha on y a certain number of time. So if that happened, then we say x and y are related, where x and y are points coming from the underlying set xn. So once this is a relation defined on the set xn, and it is not difficult to see that this particular relation is an equivalence relation, because every point relate to itself. And then if x is related to y, y is also related to x. Symmetry is guaranteed. And once you have x relating to y and y relating to z, then x is also related to z. So this relation is an equivalence relation. And the advantage of having an equivalence relation on a set is that it will partition the set into equivalent classes. And so such an equivalent classes can then be studied. So as an example, if you take this particular alpha from T8 again, one will see that when you consider 7 and apply alpha on 7, for example, under this alpha, 2 and 7 are related, because if we keep on applying alpha on 7 and apply alpha on 2, we arrive to this point 3. 7 alpha will get us, one application of alpha on 7 will get us to 6. And if we apply alpha again, we are at 3. And from 2, if you apply alpha, you get to 3. So alpha 2 will get you to 3. So that means 2 application of alpha on 7 get us to 3, and also 1 single application of alpha on 2 get us to 3. So therefore 2 and 7 are related. But then if we now consider 6 here and apply alpha on 6, we get 3. 6 alpha is 3. And then if we apply alpha again on 3, we get to 1, and apply alpha, 1 is mapped 1. So we are now at a loop. And if you keep on applying alpha, you continue to remain in the loop 1. So that means so you can never be able to get to any other point except 1 when you start from 3, apart from when you start from 6, apart from 3 and 1, you don't get anywhere else. So, and if you look at 4, if we apply alpha, no matter how many times we apply alpha on 4, 4 is a fixed point, so we keep coming back to 4, coming back to 4. So there is no way you can arrive at a common point starting from 6 and also starting from 4. So you cannot get to a common point. So therefore 6 and 4 are not related under this particular relation. So this relation is an equivalence relation, and so therefore it will partition the set into what we call orbit. Equivalent classes of the relation are called orbits of alpha. They are orbit of alpha. And if you look closely enough, you will see that this orbit are nothing but the connected component of alpha under the associated directed graph. That is the connected component of the associated directed graph induced by the alpha. We look at an example here. If you look at this particular map and see that the associated graph is this. This is the associated graph with this particular alpha. And this graph has components. It may not be connected, but it will always have connected component. This is a component of the graph here, and we have another component here, and we have a component here and a component here. And you can see that, for example, here it's not difficult to see that once you are any two points coming from a component are always related, because if I start from 1 here, I can always arrive at and also start from 7 and apply alpha 1, 2, I get to 4. And if you apply alpha 1, 2, you also get to 4. You can also get to 6. You can start from 3 and get to 4 at the same time. So all these points 1, 2, 3, 4, 5, 6, and 7, they are all related. So they form one single equivalent class under the relation theta. So this is an orbit of alpha, and this is another orbit of alpha. This is also an orbit of alpha, and this is another orbit of alpha. So this particular alpha is having 4 orbits. The first orbit is this one, and the second orbit is the other one. So actually, in the next lecture, we are going to look at this orbit very closely. Thank you very much for being with me, and I hope to see you in the next lecture, where we will talk about orbit in a more